This tiny strip of water is the only thing stopping you from driving straight from Europe into Africa. At the narrowest point, Spain and Morocco sit just 13 kilometers apart. On a clear day, you can stand on one continent and see the other. It looks like a bridge should have been built here years ago. China already has a 55-kilometer bridge and tunnel system stretching across the sea. Still, every serious plan for the Strait of Gibraltar has remained on paper. Engineers have studied this crossing for decades. Some of their bridge designs became so extreme that nothing like them exists anywhere on Earth. And once you see what building here would actually require, that short distance stops looking short. So why has this tiny crossing become an almost impossible bridge project? Well, to understand that, look at what this narrow strip actually does. The Strait of Gibraltar forms the only natural opening between the Atlantic and the Mediterranean. Southern Spain runs along the north, with Morocco facing it from the south. Ferries move between Tarifa, Algeciras, Tangier, and Ceuta. Cargo ships share the same passage with fishing boats, naval vessels, and yachts. Around 300 vessels cross every day. That's roughly one every 5 minutes, so engineers can't treat it like an empty patch of water. Of course, China built much of its crossing on bridges supported by artificial islands. Part of the road then drops into a tunnel, but Gibraltar gives engineers a completely different place to work. The first problem appears when they map the seabed. Along the shortest line between Spain and Morocco, the seafloor drops fast. Some sections approach 900 meters. For scale, place the Burj Khalifa on the bottom. Its tip would still sit around 70 meters below the waves. Engineers have to support every tower. On a normal sea crossing, piles or huge concrete foundations carry that weight into the seabed. Here, each support would rise through a moving column of water taller than any building on Earth. Oil platforms already operate in deep water. A continuous bridge carrying cars and trains requires a completely different structure, and nobody has built one at this depth. Engineers found a slightly less brutal route farther west at the Cameronal Sill. The seabed rises to around 300 meters there, but the coastlines sit farther apart. By the time the design escapes the 900-meter drop, that neat 13-kilometer bridge has already on. On top of that, the longer route still has to leave enough space for ships. Large cargo vessels need wide navigation channels, so engineers can't scatter bridge supports across the strait. A drawbridge wouldn't help much either. With a vessel passing roughly every 5 minutes, road traffic would keep grinding to a halt. Professor T.Y. Lin tried to jump over the shipping lanes completely. In 1996, he proposed a 14-kilometer bridge with several clear spans measuring 5,000 meters from one major support to the next. Turkey's 1915 Çanakkale Bridge currently holds the suspension bridge record with a central span of 2,023 meters. Lin's design demanded nearly 2.5 times that distance. Wind can bend and twist a bridge deck over a span that long, so engineers combined cable-stayed sections with a suspension system, then tested the design using computer models. Their estimated price reached $15 billion in 1996, before another 30 years of rising construction costs. Those supports would stand inside a 2-level current system. Atlantic water enters the Mediterranean near the surface. Evaporation makes the Mediterranean saltier and denser, so some of that water sinks and moves back toward the Atlantic underneath. At the Cameronal Sill, tides push these layers across an underwater ridge, creating turbulence and internal waves. That movement turns precise construction into a moving target. Survey ships must hold an exact position while drill lines hang hundreds of meters below them. Cranes would face the same pull while lowering equipment toward the seabed. The current also speeds up around each bridge support and carries sediment away from its base. Engineers call this scour, and it can slowly dig a hollow around a foundation. Crews would have to monitor and reinforce those foundations, while ships continued passing through the construction zone. Some sections contain flysch, where layers of sandstone and softer shale have folded and broken over millions of years. Other areas contain breccia, a messy mass of fractured rock pressed together underground. Quaternary sediment also fills 2 buried paleochannels near the proposed route. These ancient Eurasian valleys now sit hidden beneath the seabed, and their softer material can squeeze or shift under heavy pressure. A bridge foundation needs predictable ground beneath it. Here, neighboring supports could sit on completely different material and settle at different rates. A tunnel boring machine would face the same mess. Its cutting head could grind through hard, fractured rock before entering soft ground filled with water. Regional earthquake risk adds another calculation. Engineers can build structures that flex during shaking. They still need to predict how these uneven rock layers and buried channels will move over several decades. That pushed planners toward the tunnel idea. Before it could replace the bridge, they had to work out whether a boring machine could cross this ground without flooding. The Channel Tunnel made that idea look possible. It stretches 50.5 kilometers between Britain and France, with 37 kilometers running beneath the sea. Its builders also had one major advantage. They followed a relatively consistent layer of chalk, marl, that keeps water from passing through easily. Gibraltar gives tunnel crews much rougher ground. The proposed railway tunnel moves west toward the shallower Cameronal route. It would run for 38.7 kilometers, with 27.7 kilometers beneath the strait. The design places two single-track railway tubes on either side of a service and rescue tunnel. Cross passages would connect them roughly every 340 meters. A train leaving the Spanish coast would descend along a gradient no steeper than 3%, before reaching a low point around 475 meters below sea level. That route leaves the ships above untouched and removes the need for bridge foundations. But at that depth, water pushes against the tunnel with enormous pressure. Engineers still have to control smoke during a fire and give passengers a safe evacuation route. And before any of that works, the boring machine has to survive the ground ahead of it. Spain and Morocco have spent decades trying to figure that out. They formally began studying a fixed connection in 1979. 2 years later, Spain created Sikiza, while Morocco established Send. Both organizations focused on finding a workable route between the continents. In 2003, the two governments approved a 27 million tunnel feasibility program. The project still kept stalling. Officials updated the plans, held more meetings, and then left the idea sitting for years. In April 2023, Spain and Morocco finally held their 43rd Joint Committee meeting after a 14-year gap. Spain then allocated 2.3 million in European funding to update the research and consider building a small exploratory gallery. SESCA hired German tunnel boring specialist Heron Connect in 2024 to study whether a machine could excavate the planned route. A successful machinery study still wouldn't start construction. SESCA only has authority to conduct research. Spain and Morocco would need another agreement before crews could begin digging. They would also need railway connections on both coasts, along with border terminals and a much larger source of funding. As of right now, engineers continue updating the design. Nobody has confirmed a 2030 groundbreaking date. So overall, engineers can design a Gibraltar bridge on paper. Physics allows it. The foundations would reach through water no bridge has crossed before, while its 5-kilometer spans would be more than double the current world record. That old $15 billion estimate doesn't tell us what construction would cost today. OPAC calculated it in 1996, using a design nobody has ever built at full scale. The tunnel now offers a more realistic route. Engineers still need better geological data before either government can approve the full crossing. A smaller exploratory gallery could come first. It would allow crews to test the ground and measure water pressure. Later, that same gallery could carry telecommunications cables. For now, the unanswered engineering questions keep the bridge on paper. If a permanent connection eventually moves forward, it will most likely carry trains beneath the strait. So yeah, Europe and Africa might still end up connected one day, just probably not by the giant bridge most people imagine. If it ever happens, you may be sitting on a train hundreds of meters under the water, but would you actually get on a train running 475 meters below the Strait of Gibraltar, or would you just take the ferry? Let me know in the comments. And since you're here, this channel breaks down massive mega builds and the engineering behind ambitious architecture. Make sure to take a look at our other videos and subscribe if you want to see more projects like this.